Welcome to this explainer. Today we are decoding gRPC, the high-performance RPC framework that is literally replacing REST inside the world's largest tech companies. If you have ever wondered how Netflix serves over 3 million requests per second with sub-millisecond latency, or how Google connects tens of thousands of microservices across millions of machines, the answer is gRPC. And if you are prepping for a back-end or system design interview, you absolutely need to nail this. Let's kick things off with Section 1, the problem with REST. REST has been the dominant API paradigm for over a decade. JSON over HTTP. Simple, human-readable, ubiquitous. But here is the thing. REST was never designed for the scale modern distributed systems demand. Let that sink in. Every REST call opens a new TCP connection, serializes data into bloated JSON text, and waits for a response. JSON is verbose. Every field name is repeated in every payload. A simple integer wrapped in JSON goes from 4 bytes to over 20 bytes. Multiply that by billions of calls a day, and the waste is staggering. Then there is the type problem. JSON has no real types. Numbers are ambiguous. Dates are strings. Booleans are strings. Your client has to manually validate and parse everything, which means boilerplate code, bugs, and fragile contracts between services. And HTTP 1.1, the foundation of most REST APIs, is fundamentally limited. One request, one response, one at a time. You want to send multiple requests simultaneously? Open multiple connections. The head-of-line blocking problem is baked into the protocol, which brings us to Section 2, what gRPC actually is. gRPC stands for gRPC Remote Procedure Call. It was developed by Google in 2015 and is now a cloud-native computing foundation project. But to really grasp why gRPC is so fundamentally different, we need to look at two technologies it is built on: protocol buffers and HTTP2. Protocol buffers, or Protobuf, is the serialization format that replaces JSON. Instead of sending human-readable text, Protobuf sends compact binary. A Protobuf message for the same integer that took 20 bytes in JSON takes as little as 2 bytes. That is a 10x reduction in payload size. For a service handling millions of requests, this is not a minor optimization. It is the difference between saturating your network and cruising at 10% capacity. But Protobuf is more than just compact binary. It is a contract-first system. You define your data structures and service methods in a .proto file, then compile it into strongly typed client and server code in any of over a dozen languages: Java, Python, Go, C++, Rust, Node, Kotlin, Swift, and more. The generated code handles all serialization, deserialization, and networking. Your client calls a method that looks and feels like a local function call. Behind the scenes, gRPC serializes the request to Protobuf, sends it over the network, deserializes the response, and hands it back. You write zero networking code. Moving into Section 3, HTTP2, the transport that makes gRPC fast. HTTP2 is the second piece of the puzzle. Unlike HTTP 1.1, which processes one request per connection, HTTP 2 multiplexes multiple requests and responses over a single TCP connection. Think of it like a highway with a single road surface but multiple lanes. Streams run concurrently without blocking each other. No more head-of-line blocking. No more connection pool exhaustion. Your client can fire off dozens of requests simultaneously over one connection, and responses arrive as they become available. HTTP/2 also introduces header compression using HPACK. REST APIs send headers with every request: authentication tokens, content type, user agent strings. Over thousands of requests, those repeated headers add up. HTTP2 compresses them into a shared table, dramatically reducing overhead. And crucially, HTTP2 supports bidirectional streaming natively. This is where gRPC truly diverges from REST. Section 4. The 4 communication patterns of gRPC. REST gives you one pattern. Client sends a request. Server sends a response. Done. gRPC gives you 4. First, Unary RPC. The simplest. One request, one response. This is the REST equivalent. Most API calls fall into this category. Second, server streaming. The client sends a single request and the server opens a stream, pushing multiple responses back over time. Think of a real-time stock ticker or a live sports score feed. The client subscribes once and data flows continuously. Third, client streaming. The client sends a stream of messages to the server and the server responds once when the stream completes. This is perfect for file uploads, sensor data ingestion, or uploading analytics events in batches. And fourth, bidirectional streaming. Both client and server send streams independently. Full duplex communication. This powers chat applications, real-time collaboration, multiplayer gaming, and voice calls. The WebRTC explainer we covered earlier relies on this exact pattern, gRPC streams for signaling and real-time data exchange, which brings us to Section 5. Who is actually using gRPC in production and why? Google built gRPC to connect its internal microservices. Every Google search, every YouTube recommendation, every Gmail inbox, gRPC is the backbone. Google processes over 10 billion gRPC requests per second internally. Let that sink in. Netflix replaced REST with gRPC for its back-end service mesh. Their microservice architecture spans thousands of services, and the payload savings from Protobuf alone reduced their network bandwidth by over 60%. The multiplexed connections eliminated the connection explosion problem, where a single client calling 50 microservices needed 50 separate REST connections, consuming memory and file descriptors on both sides. Uber adopted gRPC for its dispatch system and real-time location services. The bidirectional streaming pattern is what makes live driver location updates possible. A ride can generate hundreds of location pings, all streamed over a single gRPC connection. Square, Dropbox, Cisco, and countless others have made the same transition. The pattern is consistent. Start with REST because it is simple. Hit the scaling wall. Migrate to gRPC. The CNCF's annual survey shows gRPC adoption growing at over 40% year over year. Here is the key architectural difference. REST is centered around resources, /users/42. gRPC is centered around operations, create user, get user, stream updates. REST maps to HTTP verbs, gRPC maps to procedure calls. The mental model shifts from document retrieval to service invocation. Moving into Section 6, the trade-offs. gRPC is not a silver bullet. Browser support is the biggest limitation. gRPC web exists, but it requires a proxy layer because browsers cannot speak raw HTTP or 2 frames. For public-facing APIs that need to be consumed by web frontends, REST or GraphQL still make more sense. Debugging Protobuf is harder than JSON. You cannot just curl a gRPC endpoint and read the response. You need tools like grpcurl or BloomRPC. The binary format is opaque to humans, which is an operational cost worth acknowledging. And gRPC has a steeper learning curve. Defining proto files, running code generation, managing proto registry, and versioning. It is more complexity upfront. But for teams operating at scale, that upfront investment pays back massively in reduced payload size, faster serialization, strongly typed contracts, and automatic client generation. So the crucial takeaway here is this. REST is not dead. But for service-to-service communication at scale, gRPC is demonstrably faster, lighter, and more reliable. It is not a question of if you should learn gRPC. It is a question of when your system will outgrow REST. Thanks so much for joining me today. If this deep dive gave you a clearer picture of how gRPC works, hit subscribe and turn on notifications. Keep building, and I will catch you in